There's a number that almost nobody outside a small circle of physicists has heard, and it is the number that ends the world as we understand digital security. That number used to be measured in the millions. Millions of atoms, millions of qubits, millions of years of engineering standing between where quantum computing was and where it needed to be to actually threaten anything real. And then, in the span of a few months, that number collapsed. Not gradually. Not the way technology normally improves, inch by inch, generation by generation. It collapsed because something else got involved in the process. Something that was never supposed to be doing physics. An artificial intelligence sat down inside a research pipeline, was given a broken, failing algorithm, and quietly rewrote the rules of what a quantum computer needs to exist. Nobody announced this to the public first. That's the part that should unsettle you. The first people to understand what had happened were not journalists, not politicians, not even most scientists. They were a handful of researchers at Caltech who had just watched an AI system take an algorithm so inefficient it was, in their own private assessment, roughly 1,000 times worse than it needed to be, and turn it into something that worked, something that actually physically worked. And here's where it gets worse. The fix the AI found wasn't a minor tweak. It wasn't an optimization at the margins. It was a structural discovery. Where the old approach needed somewhere between 100 and 1,000 atoms bundled together just to encode a single unit of quantum information, the new algorithm needed just 3 atoms to encode a qubit, cutting the atomic requirement for an atomic quantum computer by roughly 100-fold. Read that again. A 100-fold reduction, discovered not by a human insight, not by a decade of trial and error, but by a machine exploring a search space no human team had the patience or the pattern recognition to fully explore. This is where you need to understand what a quantum computer actually is, because the language around this topic is designed to confuse you, and confusion is exactly what lets threats grow in the dark. A classical computer, the one you're reading this on, stores information as bits, ones and zeros, on or off, nothing in between. A quantum computer stores information in qubits, which can exist in a strange in-between state called superposition, effectively letting them represent multiple possibilities simultaneously. Chain enough of those qubits together, keep them stable enough, and you get a machine that doesn't just calculate faster than a classical computer. It calculates differently. It can explore branching possibilities in parallel instead of one after another. For most of the last 2 decades, quantum computing has been dismissed as a science project precisely because keeping those qubits stable, what physicists call coherence, was staggeringly difficult. The moment you add more qubits, you multiply the ways the system can fail. That instability was the wall. That wall was the reason cryptography, the entire architecture protecting your bank account, your government secrets, and the backbone of blockchain networks like Bitcoin was considered safe for decades to come. That wall did not fall because of a bigger budget. It fell because someone tried something almost embarrassingly simple, and the results terrified the people who ran the experiment. A researcher named Robert Huang, who had previously worked inside Google's own quantum division before leaving to help found a company called Oratomic, decided to point an AI-driven optimization tool at the team's failing algorithm. The tool was called OpenEvolve, an open source system that draws on large language models, including Google's Gemini and Anthropic's Claude, to refine algorithms through a process modeled on natural selection. Think about what that actually means. This wasn't a specialized quantum physics AI built for one narrow purpose. It was a general-purpose evolutionary process, feeding candidate solutions through cycles of mutation and selection, powered by the same broad language models that write your emails and answer your questions. Huang didn't expect much. By his own account, he assumed the exercise would produce nothing useful. He was wrong. The system began generating results that surprised even the people who built it, combining prior scientific findings in ways the researchers described as genuinely novel, and showing an understanding of narrow specialized subfields of quantum computing as it tested thousands of variations. This is not chaos. This is strategy, except the strategist wasn't fully human anymore. But here's where the story stops being a curiosity and starts being a warning. Word of what was happening didn't stay contained inside one lab. According to informed reporting on the events, Huang mentioned to a contact still working inside Google's quantum initiative that he had been running AI against these problems and, in his words, seeing wild results. That conversation didn't disappear into casual gossip. Weeks later, Google quietly posted a job listing for a quantum researcher, specifically tasked with building AI-based discovery pipelines, a phrase that should stop you cold if you understand what it implies. Not a tool for checking human work, but a system designed to generate new physics on its own. And then, in a move that reads less like coincidence and more like a company scrambling to close a gap before a rival's paper became public, Google announced an entirely new internal atomic quantum computing initiative on March 24th, just days before both Google and the Oratomic team published their competing research within the same week. Two of the most advanced technology organizations on the planet were racing toward the same discovery at nearly the same moment. And the thing that got them there first wasn't more funding or more physicists. It was an AI system quietly doing the exploratory work no human team had the bandwidth to attempt at that scale. What most people are not seeing is the scale this unlocks once you translate it out of the lab and into engineering reality. Reducing the atoms required per qubit by 100 times doesn't just make quantum computers a little more efficient, it fundamentally changes what is physically buildable. The Oratomic team's follow-up research made the implication explicit. A fault-tolerant, genuinely useful quantum computer, the kind that could reliably run complex calculations without collapsing under its own errors, could plausibly be built using roughly 10,000 reconfigurable atomic qubits, a dramatic drop from previous engineering estimates that had put the requirement in the millions to 10,000. That is not an incremental improvement. That is the kind of gap that turns a 40-year engineering roadmap into a 5-year one, and it gets more concrete than theory. Researchers working alongside the same team had already physically trapped arrays of 6,000 atomic qubits in the lab, meaning the 10,000 qubit threshold wasn't a distant hypothetical. It was a number sitting almost within arm's reach of equipment that already existed, HPC wire. Now think about what a machine at that scale is actually capable of, because this is where the abstract physics stops being interesting and starts being dangerous. Every secure system you rely on, from your banking app to encrypted messaging to the cryptographic backbone underpinning networks like Bitcoin, is protected by mathematical problems that are, for a classical computer, essentially impossible to solve in any useful time frame. Factoring enormous numbers, reversing one-way cryptographic functions, classical computers would need more time than the universe has existed to brute force their way through the encryption protecting a single Bitcoin wallet. A sufficiently powerful, error-corrected quantum computer changes that math entirely. And according to analysis following the Oratomic breakthrough, a machine built around roughly 10,000 qubits, once the remaining error correction challenges are solved, no longer looks like science fiction as a tool capable of threatening cryptographic systems like Bitcoin's. This is where everything changes, because we are no longer talking about a research milestone. We're talking about a countdown, Cointelegraph magazine. And the institutions that understand infrastructure at the deepest level are not waiting to find out if that countdown is real. They are moving. Cloudflare, one of the companies quietly running the security backbone for a significant share of the internet, announced it was accelerating its own timeline for quantum readiness, moving its target deadline up to 2029. Days before that, Google made a nearly identical move, pulling its own quantum security preparation timeline forward. Read that again. These are not fringe alarmists. These are the organizations that keep the modern internet functioning, and they just told the world, through their actions rather than their press releases, that the encryption safety net protecting global digital infrastructure has an expiration date measured in years, not decades. What most people are not seeing is how quietly this shift happened. There was no dramatic announcement, no press conference declaring an emergency. Just a series of accelerated deadlines, filed almost as routine updates from the exact organizations with the most to lose if they were wrong. Here's the detail that makes this feel less like an engineering story and more like an intelligence story. According to the researchers themselves, the AI-driven acceleration behind this breakthrough was never mentioned in the original published paper. It only surfaced afterward in follow-up conversations. Oratomic's own leadership eventually confirmed it directly, stating without ambiguity that artificial intelligence had been used to accelerate the development of the technology, and that there was no question about it whatsoever. Think about what that omission means. The most consequential detail in the entire discovery, the fact that a general-purpose AI system had meaningfully sped up a breakthrough with direct implications for global cryptographic security, wasn't in the headline finding. It came out afterward, almost as a footnote in an interview. The real story is rarely the one printed first. It's the one that surfaces once someone starts asking follow-up questions. But Oratomic wasn't operating in isolation, and this is the part of the story that turns a single lab result into something closer to a geopolitical race. At almost the exact same moment, Google's own quantum division was independently publishing results from an entirely different architecture, built not on trapped atoms, but on superconducting circuits inside their Willow processor. In research published in Nature, Google's team demonstrated what they describe as the first ever algorithm in history to achieve verifiable quantum advantage, running what they call the quantum echoes algorithm, based on out-of-order time correlator computation. Verifiable quantum advantage is not a marketing phrase. It means the machine did something a classical computer provably could not replicate in any practical time frame, and the result could be independently checked. For years, quantum advantage claims had been contested, hedged, argued over in academic circles. This was different. This was a claim built to survive scrutiny, and it landed in the same window of time as the Oratomic atomic breakthrough, which means two fundamentally different approaches to quantum computing, superconducting circuits and neutral atoms. Both crossed major thresholds within weeks of each other. This is not chaos, this is convergence. And convergence at this speed rarely happens by accident. Google research. Think about what that convergence actually represents strategically. When two of the most well-resourced quantum efforts on Earth, using two entirely different physical approaches, both break through significant technical barriers in the same narrow window, it tells you the constraint holding the entire field back wasn't really about atoms or superconductors at all. It was about the sheer scale of the search space researchers had to explore to find the right configurations, the right algorithms, the right error correction schemes. And that is precisely the kind of problem artificial intelligence is disturbingly good at solving. Not because AI understands physics the way a human physicist does, but because it can try more configurations, faster, without fatigue, without the cognitive bottlenecks that slow down even brilliant human teams. According to experts tracking the field closely, this convergence between AI and quantum research isn't a temporary trend. A joint research team published work in February demonstrating what's called quantum-enhanced neural architecture search, while Google Quantum AI separately showed that its Willow processor could sustain coherence long enough to complete meaningful AI optimization tasks, and IonQ demonstrated comparable results using a competing trapped ion approach. This wasn't one lucky breakthrough. Multiple independent teams using different hardware, different methods, all crossed meaningful thresholds within the same compressed time frame. Analysts who track this field closely describe the shift with a chilling kind of simplicity. It wasn't one breakthrough, it was several complementary advances hitting at the same time, and that convergence is what makes this moment the tipping point. Now consider the feedback loop this creates, because this is the mechanism that should worry you most. Artificial intelligence helped discover a more efficient path to building quantum computers. Quantum computers, once built at sufficient scale, are themselves extraordinarily good at the exact class of optimization problems that make AI systems more powerful. Faster training, better hyperparameter tuning, more efficient exploration of neural architectures. Industry analysts following the field have described this dynamic directly, noting that better AI can help design better quantum computers, which in turn can train better AI, placing the world at the very beginning of a cycle whose potential is described as staggering. Sit with that for a moment. This isn't a single breakthrough that plateaus once the paper is published. It's a loop. Each advance in one domain accelerates the other, and there is no obvious ceiling built into that cycle yet. The scientists closest to it aren't describing it in cautious, hedged academic language anymore. They are describing 2026 as the year the entire field stopped being theoretical. And this is where the human cost of this race starts to surface, because breakthroughs like this rarely arrive without consequence for the people who make them. According to reporting on the events surrounding the oratomic discovery, the story didn't end with a clean scientific announcement and a round of congratulations. It ended with warnings. The framing used by those closest to the research was blunt. The world, according to those who understand the implications best, is not prepared for what just happened. Not prepared technically, because most of the internet's cryptographic infrastructure still relies on math that a sufficiently powerful quantum machine could eventually unravel. Not prepared institutionally, because the timeline for replacing that infrastructure with quantum-resistant encryption was built around assumptions that no longer hold. And not prepared psychologically, because most of the public, most policymakers, and frankly most technologists outside this narrow research community had no idea any of this was moving this fast until the deadlines started quietly shifting. So who actually controls what happens next? That's the question nobody has a comfortable answer for. Is it the handful of researchers at a startup that didn't exist as a company until this breakthrough justified its own founding? Is it a trillion-dollar technology company that pivoted its entire internal quantum strategy within days of hearing a rumor from a former employee? Is it the governments that are now, according to reporting on the topic, showing direct interest in these developments, aware that whoever controls the fastest path to fault-tolerant quantum computing controls a technology with direct implications for national cryptographic security, financial infrastructure, and intelligence operations that have relied on encrypted communication being functionally unbreakable? Or is it, and this is the possibility that should actually keep you up at night, none of them? Is it the AI systems themselves, not through any intention or agency, but simply because the pace of discovery has now outrun the pace at which any single human institution can fully track, verify, and respond to what's being found? The infrastructure response is already underway, and it tells you how seriously the people closest to this threat are taking it. Beyond Cloudflare and Google accelerating their internal deadlines, the broader industry is racing to build what's called post-quantum cryptography, encryption designed specifically to resist attack from quantum machines before those machines become powerful enough to matter. But building new cryptographic standards and actually deploying them across the entire global internet, every bank, Every government system, every piece of legacy software still running somewhere in a data center nobody has updated in a decade is not a fast process. It historically takes the better part of a decade just to migrate critical infrastructure to new security standards, even when everyone agrees on the urgency. And the timeline analysts are now working with a workable quantum threat arriving somewhere around the end of this decade leaves uncomfortably little room for error. Every month spent debating whether the threat is real is a month not spent migrating. Meanwhile, the underlying research keeps moving, and the momentum shows no sign of slowing. Beyond the headline breakthroughs, the broader ecosystem supporting AI quantum convergence is expanding rapidly. Major quantum computing companies are now forming direct strategic partnerships, aimed explicitly at integrating quantum computing with high-performance computing and AI infrastructure, treating the three technologies not as separate fields, but as a single converging stack. Industry researchers tracking the sector describe a broader structural shift underway as well, noting that artificial intelligence is proving essential not just to accelerating discovery, but to the core engineering challenges of quantum computing itself, including error correction, noise modeling, and precision calibration. In other words, AI isn't just helping find breakthrough algorithms. It's becoming embedded in the basic infrastructure that keeps quantum machines stable enough to function at all. The dependency is becoming mutual and increasingly inseparable. The Quantum Insider. Google, for its part, is not slowing down to let the implications settle. Public statements from the company's research division make clear they view the current progress as a milestone, not a destination. Their internal roadmap is now focused on what they call achieving a long-lived logical qubit, described as the next major milestone toward a full-scale, error-corrected quantum computer, with the expectation that many more real-world applications will be invented as that scaling continues. A long-lived logical qubit sounds like a modest technical goal. It is not. It is the specific engineering threshold that, once crossed, removes most of the remaining obstacles between where quantum computing is today and the kind of machine capable of running sustained, complex, error-free calculations at the scale needed to threaten modern cryptography. Every public statement from the teams closest to this work treats that threshold not as a hypothetical future goal, but as the next item on an active roadmap. And that raises the question nobody in this story has fully answered yet. If AI systems were capable of discovering a 100-fold efficiency improvement in atomic qubit encoding almost by accident, almost as a side experiment that one researcher didn't expect to work, what happens when that same class of AI system is deliberately, systematically pointed at the remaining bottlenecks? What happens when discovery pipelines like the one Google is now openly building are running not as isolated experiments, but as continuous, automated research processes, testing thousands of configurations a day, every day, without the human limitations that have shaped the pace of scientific discovery for centuries? The teams involved in this story are not speculating about that future. They are actively building toward it right now, in real time, while most of the world is still trying to understand what a qubit is. What we're left with is not a clean resolution. It's a set of open questions with consequences too large to ignore and too uncertain to fully predict. Will the cryptographic migration currently underway move fast enough to stay ahead of the machines being built to break it? Will the next AI-assisted breakthrough come from a company willing to announce it immediately? Or will it, like this one, only surface months later in a follow-up interview, after the strategic advantage has already been quietly banked? And perhaps the most unsettling question of all, if artificial intelligence can already accelerate physics discovery to the point where a 100-fold structural improvement gets found almost by accident, what does it mean that the systems capable of doing that are becoming more capable, not less, with every single month that passes? Nobody currently working on this technology has a confident answer. What they have, by their own admission, is a warning that the world is not prepared and a countdown that started before most people even knew it had begun.